In this video, we're going to look at non-homogeneous second-order differential equations which involve boundary conditions. So what we're going to do is solve the auxiliary equation, which is m squared minus 1 equals 0. M squared equals 1, therefore m must be plus or minus the square root of 1, hence m is plus or minus 1. In other words, we can write this as m equals 1 or m equals minus 1. So our complementary function must be in the form y equals a times e to the x plus b times e to the minus x. Now notice that our particular integral cannot contain a times e to the x or b times e to the minus x. Now, if you notice on the right hand side, we've got 2 e to the x as in a constant times e to the x, and we've learnt in the previous video that that cannot happen, because when you differentiate it, if you like to find the first and second derivative and substitute it back into your differential equation, it will make it equal to 0, and you can't have that. So our particular integral would take the form y, so we're going to assume that the particular integral in question is going to be y equals to c x e to the x. So we can differentiate this to find dy by dx, and I've shown this in previous videos. We have to use the product rule. So it's c x times e to the x differentiated plus e to the x times c x differentiated. So we just get c x e to the x plus c e to the x differentiated. So d2y by dx squared, again using the product rule, it's going to be c x times e to the x differentiated plus e to the x times cx differentiated, plus this will just give me c times e to the x when you differentiate that. So now I end up with the following. I just get cx e to the x plus c e to the x plus another c e to the x, and that just gives me cx e to the x plus 2c e to the x. So now that I've got that, I can now substitute that into my differential equation. So I get cx e to the x plus 2c e to the x. And don't forget, it's d2y by dx squared minus y is equal to 2 times e to the x. Well, our y is our particular integral, so that's going to be minus cx e to the x, which is equal to 2 times e to the x. So cx e to the x minus cx e to the x simply gives me 0. So I get 2c e to the x is equal to 2 e to the x, hence c must be equal to 1. So I can write my particular integral as the following. The particular integral is y equals cx e to the x. In our case, y is 1x e to the x. So the general solution will take the following form. It will be y is cf plus pi. So we could write this down as the general solution will be a e to the x plus b times e to the minus x plus the particular integral, which we know is plus 1x e to the x. But now, if we go back to our question, it says that we've got some boundary conditions that y equals 0 and x equals 0, and also dy by dx equals 0. So if we were to substitute y equals 0 and x equals 0, first of all, so we can say when y equals 0 and x equals 0, we would end up with the following, using this equation here, that 0 is equal to a times e to the 0 plus b times e to the minus 0. Well, we know that e to the power 0 is just 1, so we just get our first equation, which is a plus b equals 0, which is our first equation. Now, if we differentiate what we've got for y, so it's going to be dy by dx. Well, the differentiation of e to the x is e to the x is a constant, so we just get a times e to the x. But be careful here, we get minus b times e to the minus x. And here we have to use the product rule for the pink term, so it's going to be plus x times e to the x differentiated plus e to the x times x differentiated. So what I end up with, so now I've differentiated my function, I can now do the following. I can say that, okay, we know that when x is 0, dy by dx is 0. So we can say when x is 0, dy by dx is 0. Because they've given these boundary conditions in the question here. So what we can say is that dy by dx 0 a times, I'm just going to write e to the 0 here so you can see what I'm doing, b to the e to the minus 0. Anything times 0 is 0, so x is 0, that goes to 0, plus e to the power of 0. So then what we end up with is 0 is a minus b, e to the 0 is 1, so we get plus 1. So our second solution, or our second equation really, is a minus b is equal to minus 1, which is our second equation. So I'm going to write equation 1 underneath it and solve it simultaneously, which is a plus b equals 0. So a plus b equals 0 is our first equation. So we can add both equations together. So we get 2a equals minus 1. A is minus a half. And we can solve b and say minus a half plus b must be 0. So b is a half. So we could write our general solution out again, which is going to be a e to the x plus b e to the minus x plus x times e to the x. So required general solution therefore is y is minus a half e to the x plus a half e to the minus x plus x e to the x. Here's a question for you to try. You can pause the video and when you're done I will go through my work solution. Okay, welcome back. So we solve our auxiliary equation, so we get m squared plus 5m plus 6 equals to 0. So we get m plus 3, m plus 2 equals 0. So we get m equals to minus 3, or m equals minus 2. Okay, so we're going to assume that our particular integral will take the form of y equals c times e to the x, because on the right hand side we've got something in the form of e to the x, and notice in our complementary functions it's e to the minus 3x and e to the minus 2x, so it's fine. So we can use the form c times e to the x. So dy by dx will simply give me c times e to the x, and likewise for dy by dx squared is c e to the x. So we're going to get c e to the x plus 5 times dy by dx. That's 5 times c e to the x plus 6 times the particular integral. Now that's equal to 12 times e to the x. So we get 12c e to the x is equal to 12e to the x. Therefore c must be 1. So we can say, therefore, the particular integral in the form y equals c e to the x, in our case, is going to be y equals 1 times e to the x. So our general solution is always in the form of the complementary function plus particular integral. So in our case, y is a times e to the minus 3x plus b times e to the minus 2x plus 1 times e to the x. So we want to differentiate this now. So we get dy by dx, and that's going to give me minus 3a e to the minus 3x minus 2b e to the minus 2x plus e to the x. Now our boundary conditions are dy by dx equals 0, y equals 1, x equals 0. So if we put y equals 1 and x equals 0, first of all, so when y equals 1 and x equals 0, we get 1 is, we know that e to the power 0 is 1, so I'm going to assume we know that, so we can say a times 1 plus b times 1 plus e to the power 0 is 1. So we get 1 is a plus b plus 1. The 1's cancel out, so we get a plus b equals 0. Conditions are when x equals 0 and dy by dx equals 0. So we know what dy by dx is. It's minus 3a e to the minus x minus 2b e to the minus 2x plus e to the power of x. So it's minus 3a minus 2b, because don't forget e to the power 0 is 1, and then we get plus 1 equals 0. Plus 1 equals 0, so I can say 3a plus 2b is equal to 1. That's our second equation, and we know that a plus b from equation 1 is 0. So I'm going to times equation 1 by 2. So we get 2a plus 2b equals 0. That's our third equation. And then let's write the second equation underneath that, which is 3a plus 2b equals 1. and then we're going to do equation 3 minus equation 2, which will give me minus a is equal to minus 1, therefore a is equal to 1, which implies b must be minus 1. So what we can do, we can rewrite our general solution out. So we know that y is a times e to the minus 3x plus b times e to the minus 2x plus e to the x. And in our case, we're going to get that a is 1, so we get 1 times e to the minus 3x. B is minus 1, so we get minus e to the minus 2x plus e to the x.